Chapter 6, Number 6. What is the minimum horizontal force F needed to make the box start moving in Figure 632? The coefficients of kinetic and static friction between the box and the floor are 0.24 from UK and 0.41 from US, respectively. So the plan of attack will be to figure out what size value for F will give us the maximum frictional force, the maximum resistance that can happen, so that it starts to slide. Because we know that the frictional force, F sub S, will be less than or equal to mu S times Fn. And so there's a maximum value it can have, and we're going to be interested in using the maximum value. We're going to be wanting to take what is the case when they are equal, when Fs equals Fs max. To do that, we need to, of course, draw a free body diagram and then talk about what forces we have. So we'll take, this is the box. It's not a great picture for the box, but whatever. And we know, as always, that there is a weight pulling down, and that means there must be a normal force pushing back up. If we're pulling the box to the left with force, the given force F, the thing we're going to be looking for, then there must be a frictional force which is pushing back to resist that motion. And then on top of all of that, they decided to throw in yet another force, which sort of just an extra annoyance, I suppose, but which comes in at some angle, and I'm going to break into an sort of F pushing Y and then an F pushing X, where the idea is that this is the pushing force, 16 newtons, but we're going to break it into its vertical and horizontal component and put them on the free body diagram that way. And then all of these things need to balance out so that the box doesn't slide, which means so that the acceleration is 0. So we're going to go in each direction, and we're going to make the forces add to 0. All right, so from the free body diagram, we have that the sum of the forces in the x direction is, and we see here that we have the force we're looking for, and of course we have the pushing force, but only its horizontal part, and we have the static frictional force. But if we consider that this is going to be our plus direction, which makes sense, then we're going to pick up a minus sign for the frictional force because it points the other way, and we pick up a minus sign for FPX because it points the other way. In similar vein, the sum of the forces in the y, again from our diagram, we end up with Fn, Fg, and Fpy. So we have Fn and Fg and Fpy. But we want to look at this carefully and again see that if Fn is taken as our positive, then Fg points downwards, so it should come in as negative, and Fpy points downwards, so it should come in as a negative. So that's our diagram-based equation. And then, of course, we also have, from just Newton's second law, we have that the sum of the forces in the x direction is the mass times the acceleration in x direction, but the acceleration is 0, so the mass times it is also 0. And then we also have the sum of the forces in the y direction is the mass times the acceleration in the y direction, but the acceleration in the y direction also 0, making MAY 0, and so we have that. And then now we have, since we have two things that are equal to, for instance, sum of the force Fx, we can set them equal. And likewise for Fy. So we can go up here and we can say, oh, well then we must have equals 0 and equals 0. So now we can do some substitutions. If we have that equation, we can say that implies sort of that F equals Fpx plus Fs. And then likewise we could find that Fn is Fg plus Fpy. Now we're going to do a couple of substitutions that are sometimes called constituent relations, meaning they don't really come from Newton's law, they come from other things we know. For instance, we know that Fg is just m times g. And we know from our triangle, at least we can figure it out, we have this, and we know this angle, and we want Fpy and Fpx given Fp. So we can say things like cosine of theta is the adjacent side over the hypotenuse, which means that Fpx is Fp cosine of theta. And then it always comes in pairs, but sine would be the opposite side over the hypotenuse. And so Fpy is Fp sine theta. And then a whole different thing, we also know that the Fs is going to be equal to its maximum possible value because it's just about to slip, so we can't make F any larger. If we make F any larger, Fs would have to be larger and it would break. So we have that this is the maximum value, which is μs times Fn. So these things basically will clean up the other equation in a bit. So then we can start substituting in. We can say that this is Fp cos theta plus mu Fn, and that Fn is mg plus Fp sine theta. And we've taken care of the downward already with our minus signs, and the leftward with our minus signs. That allows us, remember that this is Fn, so that allows us to plug in this up here. So we're left with Fp cos theta plus mu s times mg plus Fp sine theta. And oh my goodness, is that a lot of weird symbols, but we know all of them, so we can just grind forward and do it. For instance, Fp was 16 newtons, and we'll have cos of the angle, which is 55 degrees. And then we'll add into it the static frictional coefficient, which is 0.41, times, and then we have mg, which was 28 kilograms, times 9.81 meters per second square, and then back to Fp, which is 16 newtons, times the sine of 55 degrees. So lots of ugly numbers, but all known, and so we can just throw them into a calculator to get 127.17 newtons, which, with the fact that we only have 2 sig figs, means that we really just get 130 newtons at the end. That's a pretty long way to go for a not particularly fancy answer, but that's what comes out. So it's believable with the scale of the problem.